Hello everyone. Today's practical class will be on verification of Beer's law. So, colored solutions they have the property of absorbing light of definite wavelength, and amount of light absorbed or transmitted by a colored solution. It is in accordance with the Beer-Lambert's law. But today we are going to focus on Beer's law. So what does Beer's law say? Beer's law, it states that when a parallel beam of monochromatic light, when it is passed through a solution, the absorbance of the solution, it is directly proportional to the concentration of the substance in the solution. So what do you mean by monochromatic light? Monochromatic light means light of single wavelength. So when it is passed through a solution, the absorbance of the solution, what do you mean by absorbance? It is the it measures the capacity of a substance to absorb light of a specified wavelength, of a single wavelength that we are going to use. So the capacity to absorb the wavelength, it is the absorbance. That absorbance of the solution, it is directly proportional to the concentration of the substance in the solution. So in order to verify this, we are going to use a colored solution. What colored solution? A blue colored solution. What is that we are going to use? We are going to use copper sulfate solution. So the aim of today's experiment, it will be to plot a graph of different concentration of copper sulfate solution against its absorbance. This is the aim. And then now the apparatus required. First of all, we will be using a cubit, and then a colorimeter. The colorimeter, the instrument that you have been taught in the previous class, and then copper sulfate. Copper sulfate, we are going to use 5 different concentration. The first one is 0.1%, second one 0.2, 0.3, 0.4 and 0.5% copper concentration. For copper sulfate solution, we are going to take a stock, and from that stock solution we are going to mix up the stock with the distilled water in different concentration so as to get this concentration of 0.1, 0.2, 0.3 and so on. This I am going to explain in the practical part. And today's experiment principle will be the absorbance of substance in a solution producing color. It is directly proportional to the concentration of the substance present in the solution. So the color intensity developed, it is measured by using a colorimeter, and it is compared with that of the standard solution. So coming to the procedure. For this, we are going to take distilled water. Distilled water, it will be taken as blank. We are going to measure, first of all, the distilled water using the cubit. We are going to measure in the colorimeter, and then after setting that, we are going to measure the 5 different test tube. That is for 0.1, 0.2, 0.3, 0.4 and 0.5% copper sulfate solution. And for that, we are going to fill up the cubit, and then one by one we are going to measure. It will be done using green filter of 530 nanometer. So the result that will be coming will be the optical density, or in other words, the absorbance of the particular solution. So for the green filter, it has been mentioned in the book that we should be using in 530 nanometer, but for the particular colorimeter that we are going to use, the marking is set at 540 nanometers, so I'm going to set in the practical part at 540 nanometer. And then after the practical, after measuring the optical densities of the different solution, we are going to plot a standard graph of copper sulfate by taking the optical densities. The optical densities will be getting after the practical, and then we are going to plot the optical density against the concentration. The optical density will be plotted in the y-axis and then the concentration in the x-axis. Coming to the practical part, I have prepared copper sulfate solution stock, and then I have taken distilled water in this beaker, and these are the test tubes. The solutions are already prepared. I'll be explaining this. And for this stock solution copper sulfate, I have taken 1 gram of copper sulfate in 100 ml of distilled water. Like that I have prepared. And then this is the distilled water that I'm going to use as a blank, and with this micro pipette, which is of 1000 microliter capacity equivalent to 1 ml, I'll be taking the solutions, the stock and distilled water, to fill up the test tubes. Like this I have taken distilled water, and these are the test tubes I have already prepared, and with this micro pipette I have taken distilled water from the distilled water beaker, like this, and then this I'll be using as blank. And this is the first test tube that I'm going to test. In this I have mixed 1 ml of copper sulfate with 9 ml of distilled water. We have to mix this with, and then this is the second test tube. In this 2 ml of copper sulfate with 8 ml of distilled water. This is the second one. And then for the third test tube, 3 ml of stock solution and 7 ml of distilled water. Likewise for the fourth, 4 ml of stock with 6 ml of distilled water, and then 5 ml each of stock and the distilled water for the fifth test tube. I'm going to measure this in the optical density. I'm going to measure in a colorimeter the wavelength that will be 530 nanometer, and then I'll be using a cubit for measuring this. So this is the cubit I have been talking about. So this cubit I'll be measuring the optical density of the solutions in this test tube. And in this cubit there is this is the distilled water I have taken, and then I'm going to fix the wavelength at 540. For this particular colorimeter it has 540, so I'm adjusting at 540. It has a white mark here, and this white mark, it should correspond with the knots in the colorimeter. So this, and after this I have to press at the blank for measuring the distilled water optical density. Likewise, yes, it is 0.00 I have set. For the first test tube the optical density is 0.01, and then this is for second test tube, that is for 0.2% copper sulfate solution. So the optical density is 0.02, and then this is for the third test tube 0.03, and then for the fourth test tube 0.04, and for the fifth. So in observation, for a concentration of copper sulfate solution 0.1%, we get optical density 0.01. This is for the first test tube, and for the second test tube with concentration 0.2%, the optical density is 0.02. And for third test tube, the concentration is 0.03%, and for that 0.3% copper sulfate solution, we get optical density 0.03. Likewise for the fourth and the fifth test tube, the optical densities value are 0.04 and 0.05. So this is the graph. On plotting a graph of optical density in y-axis and the x-axis represented by the concentration of copper sulfate solution, we get a straight line. In the x-axis, this 10 small square, it represents 0.1% copper, 0.1% concentration of copper sulfate solution, and in the y-axis, 10 small square, it represents 0.01 optical density. So, on plotting the values of concentration against optical densities, this is the straight line. This straight line. So, in the inference, on plotting the concentration of copper sulfate solution against their respective optical density, we get a straight line. And to conclude, since we get a straight line, the optical densities of the solution is directly proportional to the concentration of copper sulfate solution, and hence Beer's law is verified.